Till now, you may have believed in that the surface of a glass or mirror is perfectly flat. Well, what if I told you that isn't true? An atomic force microscopy, aka AFM, is a surface analyzing instrument. The precursor to the AFM was developed by Gerd Binnig and Heinrich Raher in the early 1980s at IBM Research Zurich, a development which then earned them the 1986 Nobel Prize for Physics. The AFM has three major abilities: force measurement, which it reveals the attraction and repulsion forces between the AFM probe and the sample; imaging, which presents the surface feature at sub-angstrom level; and lastly, the surface manipulation, which you're able to modify a surface either by a subtractive technique, for instance scratching it, or an additive technique like writing text or pattern through local oxidation point between the probe and the surface, all in nanoscaling. Speaking of probe, an AFM works by only feeling, or should I say touching, the surface of a sample with a mechanical probe, so obviously it couldn't view the color or take a video of the surface. Instead, it shows a 3D scan of the sample. Now, this is the polished gold mirror that I showed earlier, and I'll be using it as the sample to be imaged by the AFM. Note to mention that the duration of the scan depends on the scan rate setting, from less than a minute up to hours. After tweaking the settings of the AFM and also the PC, I set the scan setting to the scaling of 5 by 5 microns, which would be about 1,200 times smaller than the size of a black garden ant. And finally, I started the scan. If you consider this length 30 centimeters, you're watching a 5 by 5 micron surface of the sample, about 3,600,000,000 times bigger than the actual surface in real life. Also, this is the top-down view of the surface. Just wanted to tell anyone who didn't know that. Never mind. These are the large pieces of dust that weren't gone when cleaning the surface. As you can see, the distance between the maximum and minimum height of the surface is only 79.2 nanometers. But I wasn't satisfied. I wanted to go deeper into the surface. So I set the scan setting to 1 by 1 micron and restarted the scan. This scan was even more interesting. It really didn't look like a polished gold mirror anymore. It got even rougher, and besides, the height range is only 8.3 nanometers. This is a 90 billion times bigger version of the surface. But I still wasn't satisfied. That's why I set the scaling to 0.25 microns, which is only 250 nanometers, and again, restarted the scan. The only word that I can say in this scan is just awesome. 1,440,000,000,000 times bigger, ranging from 0 to 4.8 nanometers for the height. Out of my curiosity, I did another scan by setting the scaling to 50 nanometers. I really don't know what to say. 36 trillion times bigger for this one. I did one last scan, and I'll promise this will be the last scan, setting it to 20 by 20 nanometers and start. the last scan, I did find out that each bump on this surface are approximately 50 picometers. So if an atom has the size of 100 picometers, which it kinda does, about 5 atoms could fit in each of the bumps, which that's surprisingly awesome. And also I found out that the surface of the polished mirror is scaled 225 trillion times larger than the original surface. Wow. Anyways, so next time when you see a flat surface, keep in mind that it might be a super bumpy surface at the atomic scale. Why might? Well, it is possible for a surface to be atomically flat, but let's just talk about it in another video. Comment, like, and subscribe for more video on CHEMSANITY.